Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about inverse transform sampling. The motivation is that simulation is extremely important in data science when we're leveraging probabilistic models, as we saw when we introduced the Monte Carlo method. And simulating requires being able to sample or produce realizations from arbitrary distributions. In practice, this is done by decoupling the generation of the samples into two steps. First, we generate purely random numbers between 0 and 1, and then we reshape those numbers so they have the appropriate distribution. We're not going to talk very much about the first step. That is usually done with pseudo-random number generators, or alternatively by harvesting randomness from physical processes. It's a beautiful topic, but it's a bit beyond the scope of the course, so we're not going to talk about it, but I encourage you to look it up. We're going to focus on the second problem, which is I'm going to assume that I have some generator that gives me random numbers between 0 and 1. How do I reshape these samples so that they have the distribution that I want? Okay, so here I've generated 10,000 uniform samples. How can I change them? How can I transform them so that they have the distribution that I want? For example, maybe I want them to look exponential, for example. Our goal is going to be to explain how to simulate an arbitrary distribution from such samples. The only prerequisites are continuous random variables. As you will see, the idea involved is very clever. At least the first time I saw it, I found it a little bit confusing, but I think it's actually really clever. But it only requires simple concepts such as essentially the cumulative distribution function. Okay, so let's get to it. We want to simulate a random variable A, and we know its distribution. And what do we have? We have a uniform random variable U. And our strategy is going to be to design a deterministic function such that when we apply it to U, we get G of U, and G of U has the same distribution as A. We already saw that when we apply a deterministic function to a random variable, in most cases, for most reasonable functions, we're going to obtain a random variable. So what do we want here? We want that if we take any interval, any arbitrary interval xy, when we look at the probability that G of U is between x and y, we want that probability to be the same as the probability that A is between x and y. That's what we want. So now we can go to our uniform distribution, and we can think a little bit about what we're doing. So here, I'm just showing the density of probability for the uniform distribution between 0 and 1. When I sample, when I obtain my uniform samples, I'm going to get points that are going to be uniformly distributed here. Okay, that's what I'm going to obtain. And now I need to think, how do I map those points? In particular, I could think, what points should I map to be between x and y? Where you must imagine x as just like fixed values, like between 10 and 15. Which of these guys do I map to be between 10 and 15? Well, as we will see, it doesn't matter exactly which ones we map, but we definitely should map them so that they have the appropriate probability. The probability should be the probability that A is between x and y. So we should pick a slice of points to map to that interval. We should pick a slice of points that has probability equal to this value. That means, in the case of the uniform distribution, because the density is equal to 1, that this length must be equal to what? In order for this probability to be equal to this value. Think about it. I really recommend that you think about it because this is completely key. And the answer is that how are you going to obtain the probability? You're going to integrate. You're going to find the area under this curve. What's the area? It's 1 times the width. So the width has to be equal to the probability that A is between x and y. And we want to ensure that that happens for any values of x and y. Okay, so this seems a little bit difficult, but we're already on our way. Okay? again, we're deciding how to map these values so that we reshape the distribution of the samples that we obtain to have the appropriate distribution. And it looks like we need to, when we decide what to map to a certain interval xy, we need to map all the points that fall within some interval of width equal to the probability that A is between x and y. How do we achieve that? We will see in a moment, but at least now we know a little bit more of what we want from this deterministic function. Okay, so this is a more beautiful picture. We want to, for any interval xy, we want to pick points such that the width, they're in an interval of length probability that A is between x and y. Okay, so now let's go back to the CDF. The CDF of A, okay, this is the CDF of A. We're going to see that it's going to be super useful. Let's see if we get inspired. The CDF of A, any CDF, is going to go from 0 to eventually 1. And now let's take a look at this interval xy that we were interested in. Okay, this is the interval xy. This is where we would map these points. Okay, these points should be mapped here. So we want to find an interval between 0 and 1 that has with the probability that A is here, that we're going to map to those points. And here is where the really, really clever idea comes in. You look at this and you're like, wait a minute. I know by the definition of CDF that this point of the CDF minus this point is exactly the probability that I'm interested in. So this interval here that I'm going to color in red on the vertical axis has exactly the length of the interval that I want to map here by my deterministic function, so that I obtain the right probability for my new random variable to be between x and y. Well, if I go to the y-axis here, I realize that the y-axis goes from 0 to 1. Okay, just like the random variable, the uniform random variable is distributed between 0 and 1. And these guys have exactly the right length so that I map them to xy. So if I had a function that took these guys and mapped them here, I would be happy. And if it does that for any possible values of xy, I'm going to be super happy. So what do? I rotate this graph like that. And, okay, here I haven't really rotated it. You know what I mean? Like I exchange the axis. Rotating was not the right word, like mirror and rotate or whatever. I exchange the axis. I'm going to make the vertical axis my horizontal axis, and I'm going to make my horizontal axis the vertical axis. And now I have such a function. Okay, the inverse of the CDF, because when I do that, I just obtain the inverse, right? Instead of mapping this to this, I have a function that maps this to this. Okay, that's what that happens when I invert the axis. That function is going to do exactly what I want, because it's going to take intervals that have the right width, and it's going to map them to the right interval xy in this case, so that the transformed samples are going to have the appropriate probability. Okay, so the idea here is that I'm going to have samples here distributed uniformly here, and if I take the ones that are between f of x and f of y and I map them to xy, this probability is exactly the probability that A is between x and y, so I'm going to be able to sample from A, right? Like the samples that I obtain are going to have the right probability. Super clever idea. It looks simple once you understand it, but I don't know, I find it very cool. Okay, so let's take a step back and let's see what we have found out, because when I start drawing and putting a lot of colors and so on, I can understand how this might become a little bit confusing. We want to simulate a sample from a random variable A with a certain CDF that we know, and we want to use a sample from the uniform random variable u. So inspired by what I just said, what are we going to do? We're going to first generate a sample from u with our pseudo-random number generator. Python will give you one. And then what do we do to that sample of u? We map it through the inverse CDF, and that gives us our sample of A. And that's inverse transform sampling. It's going to work because of the graphical explanation that I just gave you, but it's always good to sanity check things with math to make sure that we're not fooling ourselves. And that's actually a good way, by the way, of finding cases where this might not work, because you cannot just draw an arbitrary curve and show that it just works for that arbitrary curve. Okay, so how do we go about proving this? We have a random variable, okay, that is of the form g of u. Okay, so actually maybe let me erase that, because there I'm writing it in terms of the samples. Oops, I wanted to erase. So let me erase. Okay, so maybe I'll go here. We have a new random variable b that is equal to g of a, and g is the inverse CDF of A. The reason why I'm writing G is because you might be a little bit confused. You see that this is an inverse CDF, and then once it's an inverse CDF, it's difficult to see it as an arbitrary function. This can happen. So it's always good to kind of abstract yourself and say, oh, this is just a function. What would I do if it was just some arbitrary function, like the square when we did this example about the voltage and the power? Let me think of it that way, and then let's see where that leads me. Okay, so if I think about it that way, I want to find the distribution of this function. I'm interested in the CDF or the PDF, but I can always get the PDF by differentiating the CDF. The CDF has a very clear definition in terms of probabilities. The CDF of b at y is just the probability that b is smaller or equal to y. So now I'm going to plug in the expression for b, which is g of u. Okay, so this is g of u, and g happens to be the inverse CDF, but it's just this arbitrary function. Okay, so it's important to bear that in mind. And now what I want to do is I want to transform this into a probability that has something to do with u, because I know the distribution of u, which is uniform, right? So it turns out that because CDFs are monotonic, if I have that, so this would be the CDF, so let me write this down, like this would be y, no, sorry, this would be y, and this would be f a inverse of some number u. If this holds, okay, if the inverse of a certain number u is below y, because the CDF is monotone non-decreasing, it's going to be true that f of y is going to be greater or equal to u. Okay, you can check that by yourself. It gets a little bit tricky if the CDF can be flat, but essentially the same reasoning holds. So this probability is essentially the same as the probability that u is smaller or equal to the CDF evaluated at y. Again, this is because the CDF is monotone non-decreasing. And now we're very happy, because what is the probability of u being smaller than this value? And again, here you might get a little bit confused because you have CDF of y. I'm plugging in the CDF of y. This is strange. Don't panic. You just put c here, okay? And you call the CDF of a at y, you call it c. What would this be equal to? Well, if c is between 0 and 1, remember that the CDF of a uniform random variable is just linear between 0 and 1, because when you compute the probability, it's just the area under the PDF, which is constant between 0 and 1. Basically, this is just going to be equal to c. Okay, whatever that value of c is. It just so happens that that value of c is the CDF of, okay, here I've done it in a slightly different way. You integrate from 0 to this c value that I was talking about. It doesn't really matter. You end up that the value is equal to c. So once you have done all the math, you look at the value that you have obtained. It's the CDF at y. What does this mean? It means that for any y, b, which again is equal to f minus the inverse of the CDF of a applied to a uniform random variable, has exactly the same CDF as a, which is exactly what you want, because now your samples are going to be shaped like samples taken from a. So we have proved that this clever idea that we arrived at through the graph of the CDF actually works. We have proved rigorously that it works. Okay, so now let's take a look at an example. Imagine that I have these uniform samples that I showed you at the beginning, and I want to generate an exponential with them, with parameter lambda. I look at the CDF, and now I have to take the inverse of the CDF. Okay, so let's say that this is going to be equal to u. So then E of minus lambda a is equal to 1 minus u. So a is equal to minus 1 over lambda log of 1 minus u. Okay, I always get these things wrong. Check it. I mean, we're going to see now if I've gotten it wrong or not. The arithmetic is not super important. I'm just deriving the inverse. I got the arithmetic right? Because minus log is a log of 1 over whatever is inside the log. So that was fine. The point is that now I get a deterministic function that I can apply to my uniform samples and reshape them appropriately. So let me go back by, and we have proved that this is going to have an exponential distribution. We've actually proved it. So now this is the function that I'm going to apply. Just to be clear, I'm going to observe samples here that are uniformly distributed and are going to be mapped to be uniform. This kind of intuitively shows you what's going to happen. Here, these values are going to be mapped like this. And here already you see that most of them, there's going to be a very high density for small values, okay, because a larger part of the interval are mapped to them. You also see how you obtain infinitely large values, right? Because as you approach here, eventually this becomes infinite. There's an asymptote there towards infinity. So with decreasing probability, you can get actually some huge values from time to time. Okay, they can get mapped over there. This is just, to gain some intuition about what is actually going on for this particular example. This is how the curve manages to reshape the distribution into an exponential. How do the samples actually look like? These are 10,000 samples from a uniform distribution. When we apply this function, we map all of them. We obtain an exponential distribution. And now just to make sure, I'm going to apply maximum likelihood here. And I see that the parameter is almost 1. I should have said here I've actually plotted this for lambda equals 1. Okay, so I obtain samples from the exponential like I want. Okay, and what we've learned today is how to generate samples from arbitrary continuous distribution, reshaping uniform samples. Thank you very much.